Good afternoon, everybody, and welcome back. My name is Carol Mandel. I'm Head of Astrophysics here at the University of Bath. It's wonderful to welcome you back to the first afternoon of the National Astronomy Meeting. And it's my incredible pleasure to welcome Professor Stephon Alexander. His background is real. It's not a virtual background, so it gives us a real sense of conference, despite the fact that we're all digitally connected. But being digitally connected, it's given us the chance to have this wonderful eminent physicist join us for NAM. Stephon is a physicist and a musician, and he's straddled the world of theoretical physics and jazz music over the last 2 decades. He works on the connection between the smallest and the largest entities in the universe, pushing Einstein's theory of curved spacetime to extremes, beyond the Big Bang with subatomic phenomena. Stephon is a professor of physics at Brown University, and he's held previous appointments at prestigious universities such as Stanford University, Imperial College London, Penn State, Dartmouth College, and Haverford College. Stephon is a specialist in the field of string cosmology, where the physics of superstrings are applied to address the long-standing questions in cosmology. He's also an outstanding communicator to the public, and he's taught the complexity of string cosmology to children as young as 5 and 6. In 2001, he co-invented the model of inflation based on higher dimensional hypersurfaces in string theory called D-branes. In such models, the early universe emerged from the destruction of a higher dimensional D-brane, which ignites a period of rapid expansion of space, often referred to as cosmic inflation. Today, it's my great pleasure to introduce his talk, The Jazz of Physics, the link between music and the structure of the universe. Stephon is going to speak to us now for about 30 to 40 minutes. Do please put your questions in the chat, and we will pick those up after Stephon's talk. Stephon, over to you.
Thank you, Dr. Mandel. It's a great honor and a great pleasure to be invited to give this plenary talk. Quite humbled, and I welcome you here from the island of Saint Martin, where I'm actually on a work vacation, while I'm working on some papers, trying to tie up some papers here, having to do with black holes and vortices and all that interesting stuff. So onward to the talk. So we're gonna now. Okay, wonderful. So we're gonna begin our talk, and I would like to get some confirmation that everyone can see my talk. Some verbal confirmation.
See it and we can hear you. Yes, all looks good.
Okay, so you can see the first From the Jazz to the Cosmos, right? The screen is large because.
Yes, that's right. We can see that.
All right, wonderful. So let's begin with this talk. This talk is mainly based on my first book, The Jazz of Physics, and my upcoming book. This upcoming book is called Fear of a Black Universe. The title has a duality. It concerns the black ideas, the dark ideas in our universe, the dark things. And, going back to the ideas of Michael Faraday that were once thought to be laughable, turns out to be the idea of the field. So the book kind of goes into the importance of theorizing, the importance of even entertaining the most absurd ideas when it comes to trying to advance our science, especially astrophysics and cosmology, given the advent of dark energy and dark matter, to name a few anomalies. So let's begin. I mean, I kind of want to couch this talk on a more personal level, which is, what does it mean to be a scientist? Many of us, we grow up, and many of us are informed and influenced by the media, by our parents, by culture, by books we have read, by all sorts of inputs that come into informing, influencing, what we are to become when we become adults. And for me, that struggle was a struggle because I grew up in New York City, in the Bronx, child of immigrant parents from the Caribbean, and music was really the thing that was supposed to be what I was told that I should do. But I was very inquisitive, and so growing up in the Bronx in the '80s, this was a struggle trying to figure out what I was going to become. And for me, some of that, I want to kind of walk you through that struggle continued on. It's not a struggle. It's not a conflict. It's more of an opportunity. The fact that I had these two things that I was passionate about, and that basically this talk is really a byproduct of throughout my life and my becoming as a scientist, ways in which I was able to reconcile that, and how it actually led and informed how music then informed the way I think about my physics. It's not the only way I think about my physics, but certainly it's an important way. And that story actually begins that, as a teenager in the Bronx, New York, I looked around me. I didn't see many scientists that looked like myself as a African-American person. Most of the people that were successful were musicians and athletes, and so the messages from the media and society said that that's what you should be doing with yourself. But the game changer for me actually was the most famous rapper at the time, Rakim, known by many to be the greatest rapper of all times, started rapping about science. And you see that he has a line from one of his most famous rap songs called My Melody. So that's what I'm saying. I drop science like a scientist. My melody's a code. The very next episode has the mic off in the start and ready to explode. I keep the mic at Fahrenheit for these MCs to make them colder. The listener system is kicking like solar. And basically, in the era of a 14-year-old kid looking for role models, he was enough, because it just made it cool for a young nerd like me to still pursue an interest in science. Another influence is Albert Einstein, because Albert Einstein definitely wore his personality on his sleeve as a scientist and demonstrated that you can be your true self and be a great scientist. You don't have to fit in to what stereotypes tell you a scientist should be like, even though now there's a stereotype of being like an Einstein. But, when Einstein was around, there was no Einstein. And another one, of course, was the subject matter. I became a professional saxophonist. I still play when I'm able to play. And John Coltrane, for me, showed the reverse, that as a musician, he wasn't limited to just playing music the way everyone else is playing it. He actually sought ideas from Einstein himself. And if we have enough time, I'll talk about this diagram that Coltrane made that was based on some of Einstein's idea of invariance. Okay, so I'm going to skip forward, but basically I lived in London. I was at Imperial College for a couple of years as a postdoc. And during that time, I befriended Brian Eno, who many of you know. He is a local hero and a global hero. And Brian influenced me because before going to work, I would before going off to work at Imperial, I would stop by his studio and we would have tea, or he would have tea and I would have coffee. And I would see him basically applying ideas of science and mathematics into his music and his art. And that influenced me to maybe be brave and entertain my music into my science. Now, let me tell you, at that point of my career, all the way through my PhD, I kept my music world and my science world separate from each other. But Brian Eno was really the first person that encouraged me through his actions that I should explore, trying to find ways, find analogies and metaphors to help me see my science and my research in different ways, meaning music. And but this is nothing new. It turns out from the very birth of cosmology itself, of astrophysics, I'm talking about pre-500 BC, Pythagoras, who came on the scene, came up with this idea. We know Pythagoras from being a person that came up with the Pythagorean theorem, but he also set up the whole Platonic and Aristotelian school that led all the way to Kepler, Galileo, basically the father of what we now know as modern astrophysics. And Pythagoras was known to coin the term cosmos. And here he believed in this idea that the motion of the planets had to do with something he called music of the spheres. And here's a paraphrase from Pythagoras. There's geometry in the humming of the strings. There's music in the spacing of the spheres. Now, Pythagoras also invented something that we now know as a modern Western music scale, using this intuition by looking at an instrument that he constructed called a monochord, which is a modern, old school version of a string instrument, like a guitar. Now, in the 1600s, Kepler was trying to understand the motion of the planets, and we all know from his discovery of Kepler's law that this had to do with elliptical orbits, that also that we live in a sun-centered solar system, and planets go around the sun. But actually, Kepler was inspired by Pythagoras himself. he first tried Plato, but he realized that Plato was a student of Pythagoras, the Pythagorean school, and he went back to the original sources. And basically at that time, and this is a very important lesson, natural philosophers like Kepler had to learn music theory. It was part of their training. So he used music theory as a tool. And as we see here in his own handwriting, he mapped out the motion of the planets by associating the orbits with musical notes. Now, there's a very nice book called Music and the Making of Modern Science by Peter Pesek, where he goes through this whole system that Pythagoras used. And that was the thing that led to his equations. So I guess what I'm saying is that this idea of using musical thinking and musical analogy into our science, and especially astrophysics and cosmology and physics, is nothing new. It's part of our tradition, actually, going way back to Pythagoras, Kepler, Galileo, and others. So the idea what I'm going to do now is to kind of spend the next couple of minutes and give you a very quick grand tour of some of the ways I've done that. Okay. And the first thing is, can we, this kind of thinking applied for planets going around our solar system. At that time, we thought that our solar system was unique, but now we know our universe is filled with structure. And what we're looking at here is a computer simulation, which agrees quite well with observation of the large-scale distribution of galaxies. And what we see when we zoom out billions of light years, we see basically a network structure of galaxies. So every dot should correspond to a galaxy or a protogalaxy. And what we see here is a superstructure, an interconnected structure of what we think to be individual isolated galaxies. And the question in cosmology is, of course, we know that the universe is expanding. We're looking at a representation of the universe today with this large-scale structure. So that means in the past, as the universe was hotter and denser and smaller, that these structures were not there in terms of the prediction of the expanding universe. In fact, the universe was actually chaotic and structureless. And we want to understand how this structure formed using the known laws of physics. And last year, the Nobel Prize was given to Jim Peebles for figuring out that physics. And what I'm going to argue is that the key, when you look at those equations that people tried to solve, of the perturbed Einstein equations coupled to cosmic fluids, there was an insight that Peebles had, and that insight was the correct physics that allowed him to solve the equation, and that physics was a physics of sound. And now what we're going to do now is show exactly, not only was the universe functioning as a system to generate sound, but I'm going to actually leave it as a little surprise to tell you that it's a little bit more musical than that. But to do that, let me just tell you that the key idea here that links, remember I talk about the link between, you might ask me, what is the link, the title of my talk, between music and the universe and physics? And that link is actually the common language of wave phenomenon. That basically waves are special in that if we look at my little slide here, not my big slide rather, we see that we have three different periodic, perfectly oscillating waves, and that they could be added together to give a complicated wave at the bottom. And that actually, there's some magic here, that if I give you a complicated wave, for those who are looking for extraterrestrial life, you're looking at very complicated radio signals, for example, and you can decompose that complicated wave through the mathematics called the Fourier transform. You can decompose that complicated wave into simpler waves. So it's like taking a complicated sentence and decomposing that sentence into words and then into the alphabet. So these periodic waves are like the basic building blocks that constitute what music is made up of, what sound is made up of, and also what the basic vibrations of the universe, the energy and the matter are all representations basically of interacting vibrational forms of energy. So let's go. And well, our best intuition for this is actually musical instruments. So if I look at blowing into a flute or a saxophone, which is what I play, or plucking a guitar string, basically pressure waves are set up in that instrument, and that instrument will vibrate and then radiate that vibration through compressed air molecules in a vibrational pattern, and then you hear that as sound or music if it's ordered sound. Now, and so this idea of the Fourier series, that basically I can take a complicated wave and decompose it into these special periodic waves, is like an instrument that can play different notes. The different vibrations, the lowest vibration at the top will correspond to, say, the lowest note or the fundamental of that instrument. That's the biggest wave that can fit into the instrument. It's really a quarter of the wave. And then if I split the wave in half, then that x divided by 2 is the octave. X divided by 3 is the perfect, is actually the third, third. X divided by x divided by third is a perfect fifth. That's one of the most consonant notes in music. A lot of classical music is based on the movement of the perfect fifth. And then we have the perfect fourth and so on. And this is basically Pythagoras' idea realized. So what am I saying here? In a nutshell, a lot of the vibrational forms we see in our universe can be understood as basically being able to be decomposed into these more fundamental vibrations, like an instrument, like how an instrument generates different notes. So each of these vibrations will correspond to a different note in your musical scale. Now, I'm being very loose with my language. This is meant to be a very rough sketch. If you read my book, it goes into 300-page of glory into these details, if you're interested. Now, it turns out another way of seeing this is to look at how an instrument actually produces notes. If we're looking at a flute here, this is an oscilloscope presenting the different frequencies when the instrument plays one note. So pay attention here. The instrument is producing one note. And on the y-axis is the loudness of that note. And on the x-axis, as x increases, that corresponds to a given periodic wave or a given note. But you should scratch your head and say, but I don't get this. When the instrument plays one note, I should only see one peak here. What becomes of these other notes? Well, good. Your ears hear the one note. That's the note that's the loudest. But the other frequencies that the instrument produces, because reveals information about the geometry of the instrument and its material makeup. And you hear that as the sound or the timbre or the characteristic color of that instrument. It's what makes a flute sound like a flute. It's what makes a guitar sound like a guitar. The other frequencies, these other higher harmonics, is what we hear as a signature sound or the timbre of that instrument. So in a nutshell, what I'm saying is that an instrument will produce one note if I'm playing one note. If it's a piano, it'll play a chord. And the thing that we hear as the note or the chord are the dominant frequencies, the ones that's the loudest. And the other frequencies that we hear reveal the material makeup or the geometry of that instrument. So now the question is, what does this say about, can we use this analogy to say something interesting about our universe and about the large-scale structure in our universe? And to that, we need to now look at this picture where Nobel Prizes were given for the picture of the baby picture of our universe. This is a picture of our universe of roughly 13.8 billion years ago, before there was large-scale structure. This is known as the cosmic microwave background radiation. And in a nutshell, what we're seeing is that the different colors here correspond to the picture I want you to have in mind here as a good analogy. Imagine the universe is basically a hot ocean filled of energy, and like basically energy of subatomic, a quantum soup of vibrating energy. And this energy is waving. It has tiny undulation, some like think about the surface of the ocean. And these tiny little undulations are going to be it's going to gravitate, because remember, gravity likes energy, and wherever it sees localization of energy, gravity would like to attract nearby regions of that energy. So what this cosmic microwave background radiation is revealing is basically a very hot, dense universe made up of a plasma of photons and elementary particles, where there's no galaxies, no stars, no structure. And as the universe continues to expand and cool, what we should expect is that those waves basically coalesce and condense to form the first stars and galaxies. But this does not look like that. This picture looks very disorganized and chaotic. And this is where Jim Peebles came in and others to show that if you analyze this through the lens of waves and sound, and you think of this really as sound waves, that the universe is really carrying sound waves. What do I mean by that? Remember, a sound wave is nothing more than an example of a pressure wave. So this plasma carries pressure, and there are different regions of higher and lower pressure. And so the question is, let's look at this through the lens of waves. And let's do that now. And if you do this, so that one picture is that to the left, we see this large-scale structure, and as time goes on, this picture shows that these tiny undulations will grow to form the first stars and galaxies 13 billion years later. If we look at this through the lens of sound, we see something very peculiar. To the red line corresponds to the theoretical prediction. So in other words, we got the physics correct, okay? Einstein's theory of the expanding universe, along with these undulations, these energetic waves, sound waves, produces exactly what we see in an instrument. We see the dominant frequency, which is the first peak. Physicists call this the acoustic peak. This corresponds to the geometry of our universe, the size of our universe at that time. It corresponds to the dominant form of energy. We call this dark energy. So what we've seen is a prediction of dark energy in the universe. The other peaks we see, like if we use the analogy of an instrument, should reveal the material makeup of the universe, like the other peaks reveal the material makeup of the vibrating instrument. And that reveals the amount of baryons in the universe, the amount of visible matter, and also the amount of dark matter. So we see a very beautiful picture that our early universe is functioning something like an instrument. And so maybe Pythagoras was a little bit correct according to this picture. Now, does it mean that the universe is producing music? Well, that's up for debate. It depends on if you're a composer like John Cage or post-John Coltrane. If you believe that music is only something that humans can perceive and make, well, my friend David Rothenberg, Dr. Rothenberg, just wrote a paper in Nature showing that mockingbirds compose music. And anyway, that's an interesting debate. I'm now going to kind of end with a little interest in speculation, and it has to do with, can we use music to understand other parts of our physical universe? And one of the things I played with as a jazz musician was, can I use my understanding and my practice as a jazz improviser to help me give ontological understanding of the physics that I work on? So for example, a lot of what I work on is quantum cosmology, applying quantum mechanics to the entire universe, quantum field theory, and things of that nature. And one of the things we do know is that while the equations of quantum mechanics are correct, we struggle with the correct interpretation of quantum mechanics. It's still under hot debate as to how to interpret quantum mechanics. Do we truly give a probabilistic interpretation all the time for quantum systems? Is there something deeper like a hidden variables theory? How do we deal with the measurement problem? And so one of the things I toyed with is, can I use some of my knowledge of jazz music to help me get a different interpretation of quantum mechanics? And what I want to play with here, and this is just playing because that's kind of what a lot of researchers would about, playing with ideas and seeing what works and what doesn't work. So I'm going to present to you another interpretation, a quantum interpretation, a jazz interpretation of quantum mechanics. So Richard Feynman taught us in the upper right-hand corner that a quantum classical particle to the left there will traverse a unique trajectory in space and time. If I throw a ball, it will traverse a unique deterministic line. It doesn't have to be a straight line, but it has to be a unique line. But the quantum particle, like an electron, what Feynman's part of his Nobel Prize was to realize that a quantum particle does not do that. Quantum particle, according to the equations of the Feynman path integral, will consider all possible paths from point A to B. Now, this is strange because it's one particle that's doing that, not many particles. So how could one particle know to traverse all possible paths? That does not jibe with our intuition. But I want us to now look at, in writing my book, I spoke at length with a great jazz musician, one of my heroes, Sonny Rollins, and he let me into something. It has to do with, jazz musician, when we learn how to improvise, when we practice improvisation, we have to have strategies, because when you're doing it in real time, you know what? If you make a mistake, you have to deal with it in real time. And human beings are not perfect, and there's no such thing as a perfect improviser. In fact, the definition of improvising, as far as my sense, is actually being imperfect and knowing how to deal with it and make that musical. So one strategy that Sonny Rollins taught me was the idea of targeting. Here's what the idea is. This is for all the jazz aficionados out there. The music can be happening so quickly that in real time and in the moment, you cannot really think about all the possible notes that's going on, okay? to play what note. So one thing that jazz musicians will do, as you see, this is actually a at the bottom corner here are some notes. You see these notes? This is a transcription of an improvisation of one of Sonny Rollins, an improvised line of one of Sonny Rollins' songs that he improvised over. And what I want us to pay attention to is not the notes in between, but the beginning note and the end note. If you look at the beginning note, that's a D, right? And the end note is a G. And one interesting thing about the D and the G is that they're harmonically related to each other, meaning that the D and the G are perfect fifths. They're related to a perfect fifth from each other. And the idea of targeting is that you target, you kind of have in mind what the target note will be downstream, and you basically improvise like notes, and you weave notes in between that. So in other words, a different improvisation, if I would have targeted the same note, I could have threaded a different set of notes in between. And the idea of targeting is that it's still going to sound interesting, right? So the idea of targeting is that you're not really paying too much attention to the notes in between, right? You are trusting that the notes are going to play in between as long as you target the first and the last note that are harmonically related to each other. You're going to get an interesting improvised line. And that every time you improvise, because remember in music, in a jazz improvisation, you get a chance to come back again because the structure, the harmonic structure of the music will repeat itself. It will cycle itself like the 12-bar blues. Every 12 bars, the music will repeat itself, and you'll get another chance to improvise a different line. So the idea here maybe that is that maybe what quantum particles are doing is, if you think of the initial and the final point in the quantum particle, if I go back to my picture at the top there, that maybe what the electron is doing, a quantum particle like the electron or a quark, is that it improvises from point A to point B. Okay, so I'm gonna now end my talk. There's a lot more I could talk about, but I kind of want to leave on this platform some time for questions, comments, and a conversation. Thank you for your time. It's a real honor, and I hope to see you all soon. England is one of my favorite places to be. I spent many years there, so I look forward to coming out there and visiting friends, especially now my new friends at the University of Bath. Thank you.
Stephon, that was absolutely fantastic. Thank you for that whirlwind tour of the intersection between jazz and physics. We're just gathering up the questions now from the chat. And as they start to come in, I'd really like to sort of open this conversation up a little bit. I've got lots of questions in my mind. And I'd be really interested to understand, how you developed your ideas of cosmology. And you've got that incredible musical background. And, how did you approach that? I'm thinking of sort of the young scientists who are on the call right now. They may have gone through sort of very classical scientific training. How do you approach something as esoteric as cosmology and quantum physics and start to find a way through?
Yeah, the first thing I'm going to say is that you can do it. I remember when I was a student I was dreaming about what I was going to become, and I kind of thought, well, maybe I'm not smart enough to do this. And I think one of the things that's important I remember there was a young a string theorist that I spoke to, and he said, you can do this. If you put your mind to it, you can do this. So the first thing is that you can do this. And I'm not saying that in some naive way. I'm actually very serious about that. So in my case, I think the important thing is to recognize your unique strengths. It is important to develop, to continue to develop a basic foundation. So, you want to have an underlying foundation and realize that everyone has their own path in developing that foundation. Some might develop it faster than others. I'm pretty slow, right? And that there are many ways to develop that foundation. And we're different types of learners, right? And the other thing is, do not be afraid of talking to others in different fields. Some of the greatest ideas in my second book, Fear of a Black Universe, I kind of surveyed that some of the greatest ideas in our science came because people spoke to people who they were told not to speak to, right? So, sure, some of the founders of quantum mechanics were deeply involved in Eastern philosophy, Eastern mysticism. Schrödinger, Max Planck, Niels Bohr, I mean, it goes on. Von Neumann, the mathematician, talked about. So don't follow what the ideas of what people say. This is what a scientist should be like, talk like, and look like. You are your own self, and I think that it's really important moving forward. I think the breakthroughs are going to come from those who bravely embrace themselves and be their true selves, develop that strong foundation, and then venture out and talk to others who you're told not to talk to.
I love that idea, Stephon. I think that's great, that diverse pathways into science. And, being a maverick and speaking to people that you're told you're not allowed to. I mean, on the Eastern mysticism side, I mean, what struck me as you were giving your talk, of course, the history of Western music really changed, I guess, in the, around the time of Bach with the well-tempered scale. But before that, of course, we had lots of tiny intervals between a classical semitone. I mean, in an analogy with that infinite series that you showed from the cosmological perspective, are we missing something without, going to the Eastern style music where there are many other tones that our Western brains are not attuned to? Again, another analogy with physics.
That's a great question. I mean, that's like a third book. Yes, I mean, obviously music is things that we perceive, that we hear. I mean, we have 5 senses, and so we hear music. But, I saw this amazing TED talk where a deaf person said, I can hear music too. I feel the music. And so there again, like if we now expand what we mean by music, right, to a more general, that we as human bodies, as human beings, we interact with our universe through our senses, whether or not we are like, there's some cognitive scientists, people like Ed Large and his people who I talk to, who kind of see the human mind, the human brain as more of an antenna to the universe, right? And we take in and put out information. And so it's a very good question. It's a very deep question. And the other thing too is that there's a universality. I mean, just because, this chasm, this divide between what we call Western music, and my friends who study this, musicologists, actually, there's really, there's one humanity, there's one, and different expressions of how music and musical system, but it's basically how instruments vibrate at the end of the day. And whether or not it's an African drum or it's in what have you, we know, right? One of my favorite producers, a guy named Nitin Sawhney, who's based sometimes in England. The Asian dub the beautiful thing about music is its compatibility from different sources of music from all around the world to come together to make new music, right? So,
and it feels like interdisciplinary science. Yeah.
Interdisciplinary science. And, we talked about words like diversity. I also like to use the word variety. If I give you a variety, a variety of things to choose from, why limit yourself to one way of thinking? One way, if it works, continue to use it. But there are a variety of other things that you can draw from. And that's where I see how I do science and how I do cosmology. It's a tool, like all the other tools that I have at my disposal. And there's another tool. If you're a painter, guess what? That's going to be a tool to your disposal. If you're a linguist and you're a scientist, so we have all these other tools that we can draw in, a variety of tools to do our sciences, because we're the ones that are trying to understand the universe. The universe understands itself. So the more the merrier, right?
Yeah, absolutely. And you've got questions pouring in now that you've really triggered on the whole sort of music astrophysics point. Let me just flip across a little bit to you personally, your career, because I have a great question here. How do you balance your music and astrophysics careers that you've done both to really high eminent levels? Both require a lot of commitment, dedication, and investment. How have you managed that balance?
Yeah, so I would say it's not a balance. It's actually what I do. In other words, like, one can't really exist without the other. So it's sort of like, it's a good question, by the way. So, so it's like saying, how do I eat my breakfast without brushing my teeth in the morning? I could do it, but of course, so it's sort of like, if I find that playing my instrument and being involved in music, not really enhances my ability to do science the way I do it, and vice versa. And so for me, it's kind of part of who I am, and it's not it's not this balancing act that I do to try to do one and the other. The point is that it's one whole thing. They need each other.
Yeah, it's great. And it's related to that, a great question from Simon Josie here. Do you find yourself getting new science ideas when you're in the middle of playing, for example, at a jazz gig, or is your mind solely on the music? And then I guess vice versa. You know, do you get musical ideas when you're doing your physics?
That's a great question. I would like to say that, yeah, when I play this magical thing happens where I feel the universe, you know, every once in a while that might happen. But I think it's more to do with like saying that if I go on a nice long walk or a hike, you know, and then I come back home and I take a shot, whatever, and then all of a sudden, like I am ready to take in ideas, right? So I see my playing music as a kind of more of a ritualistic thing. It's like it helps prepare me and my mind to now really be open and take in ideas that I'm going to pursue, or even be ready to actually engage in my science.
Yeah, that's great. I mean, and related to that, you mentioned about Coltrane's Einstein Inspiration. Can you say a little bit more about that for us?
Sure, I'd love to do that. So it's actually a really nice story. So David Amram, who I met, who is a great composer, Hal Bernstein made him the composer of the first composer of the New York Philharmonic, and he and Coltrane were friends. He played also with Dizzy Gillespie, and he told me the following story about Coltrane. He said that one day he was in an intermission at Cafe Bohemia. It was a jazz club in the Village, and in New York. And Coltrane was sitting outside, and you know, the intermission, and he and Coltrane were talking. And because he was a composer, Coltrane was a music theory nut, so they were kind of soundboards to each other. And he said Coltrane asked him, David Amram, "What do you think about Albert Einstein?" And David Amram understood that to tell Coltrane, "What do you think about Albert Einstein?" And Coltrane then went off. David Amram said he went off on everything about Albert Einstein and his theory of relativity and his idea of space and time and invariance, and that he understood what Einstein was trying to do, and that he wanted to do for what Einstein did for space-time, he wanted to do that for music. And so when I looked at Coltrane's diagram, I immediately, for that piece of information, I was trying to understand Coltrane's diagram for years. It was like, it was presented as a mystery. No one understood it because he didn't tell anybody. And then when I saw that he was studying Einstein, that we know that the key idea behind Einstein, the Einstein program, not only for relativity, but for all of physics, for theoretical physics, is the idea of invariance and how invariance leads to symmetry principles. And right, so you change something and it looks the same. So therefore there's an invariant, right? I change coordinate systems, the speed of light is the same. That's invariant. That change in things is a symmetry transformation. So there's a link between a symmetry and an invariance, right? If you look at Coltrane's diagram, there's a lot of symmetry there, symmetric patterns, right? Of how you may change that diagram, and it ends up looking the same. And so that was basically a practice system for him to practice, and also for him to generate ideas. And then if you see his albums like Giant Steps and A Love Supreme, and this, you can see that some of these ideas played out in his compositions itself.
I mean, it's incredible to think of that, because the conceptualization of general relativity is, it's not trivial when you learn the maths, if you do it through tensor theory, but actually stepping away and thinking of it in a very different way. It's incredible to think of that. And we have lots of questions on the chat.
Way.
Yeah, exactly. I mean, there's lots of questions in the chat really about that communication of science to the public, and, you know, thinking about some of the fundamentals. Are we missing something? Is our neurology and, you know, the neurology of our brain, is it particularly attuned to simple harmonic motion, which of course we use to solve equations across different fields? Is there some sort of underlying principles? But I'd be really interested to hear your experiences of explaining these really complex ideas to children, because I saw your YouTube video where you were speaking to really young children about string theory. And string theory for all of us as scientists, it's the frontiers of physics. So how do you find working with children? Are they able to come to these really complex ideas much more flexibly than adults, for example?
I would say I wouldn't. It's hard to know that, but I would say that. I mean, for me, it's more of you want to get them their interest, you want to pique their interest, and you want to meet them where they're at, and by the way, meeting them where they're at is not necessarily you know, anything less, or just meeting them where they're at. And where they're at is their direct access point as kids is music. They know a song, they know they've probably played with some kind of instrument. So that's their access point. And that access point, which is a musical instrument, I pick up the instrument, it's tactile, you can see it, you can interact with it. It's not some pie in the sky idea there. And you know, a lot of the physics in string theory, at least classical string theory, is just hearing a guitar string when you pluck it. So again, in general, I think when we communicate things to each other and to the public, I really do. I see myself as a dumb physicist. I'm a dummy, really. I'm not saying that. For me, being smart is being as dumb as you possibly can. You know, can I understand something as simply as I possibly can, right? Because whatever's going on in my brain is doing really complicated things, right, to make something simple, right? So
yeah.
if I can like let the brain do that part, if I can understand something as simple as so a lot of my work is actually trying to understand things as simple as possible. Like, for example, Einstein's theory of tensor calculus. What if I tell you that I can teach a graduate level course with that without any of the tensor calculus, and then we can bring that in later on? There's a simple way to do this, and I think really great physicists are able, the ones I know, were able to do that, see clearly and simply.
Yeah, absolutely.
And we use our direct experiences to access. I'm curious, Carol, if you see it the same way, or if you have, how do you do it?
Well, I do. I mean, I suppose I learned general relativity with tensor theory, and I was, you know, the way we were taught, of course, was we had to learn this new maths. And so it gave me no physical concept of actually what those equations mean. But when you write them simply, and then you step back and you see them as the fluid equations, then you can start to really conceptualize what they mean. I mean, I'm really interested as well, you know, the fact that we've got only three exact analytical solutions to Einstein's equations, and then everything else are numerical approximations. And we've got scientists around the world using supercomputers to find those solutions. Do you think there are other solutions? Again, you know, back to this analogy with music, you know, where is the next step? Should we still be looking in Einstein's equations, or should we be looking for that bigger, all-encompassing theory?
That's a good question. I think we should do both. We should do both. I mean, you know, my style these days has evolved. I went from just living in 10 dimensions to being a minimalist, actually. So can I strip down a theory to, you know, the most minimal ingredients and get the most out of it, you know? Okay. And so, you know, I don't want a car that can do everything, you know, everything, like it can fly, it can do all these things, it has a great, but it can't drive from A to B, you know? So I don't, you know, as my friend Sabine Hassenfelder says, you know, we don't want to be lost in math.
Yeah, exactly. So, I mean, it's an interesting comment that you make, because I think, you know, I'm an observational astrophysicist, and I guess we're now going into a whole new era. Thinking about your analogy with doing live improvisation in the moment, you know, we're now going to be reaching an era where we have a deluge of data, and actually it will be much more challenging to have that simple intuition. I guess many of us who are, you know, old, we've gone into our own data, we've studied maybe one galaxy or one transient star, but actually we'll now have a deluge of data from instruments like Square Kilometre Array and the Large Synoptic Survey Telescope. We've got gravitational wave data pouring through, and we're actually opening up the transient universe. So, you know, my feeling is that we need some testable predictions from our eminent theorists, so we can now go into these vast data sets, almost like particle physicists, and, you know, ask a question of the data sets. You know, do you think that's going to come from string theory, or do you think that, you know, do you see on the horizon some really strong experimental testable predictions coming out of the theories that you work on? Or how far away are we from that?
So you know, yeah. Well, I am optimistic about that, but you know, I'm optimistic but realistic. What I mean by that is that I think our era has been, of scientists have been spoiled, because, you know, we spent like 2,500 years just figuring out the laws of motion, leading up to Newton, right, from Pythagoras to Newton. And then, boom, there's this huge explosion of relativity and black holes and all this good stuff. So are we going to have the same fortitude in the next decades as we did before? I'm realistic. I'm optimistic in the sense that we need the data. We need observation. Astrophysics and physics is an experimental science, first and foremost. Theorists, our job is to we're not doing physics. My friend, the other day I had this friend goes, I'm quite a mathematical strength. I was like, well, you're not a physicist then. You know, you're a mathematician. You're not our job is to, you can't hide behind your math, man. I said that, you know, you have to do everything in your power to make some kind of connection, even if your theory is really way out there. Try, right? And so, I can only eat my words, and everything that I've worked on over the last 5 years, I would say 90% of what I've worked on has some ways of trying to make contact with observation. One thing I have to tell you that I'm interested in is, you know, it's the following: all the four forces that we know, one of them is special and also responsible for life as we know. It's called a weak interaction. Stars burn because of the weak interaction. But what's the simple thing behind the weak interaction that makes it special and different from the other three forces is that it violates left-right symmetry, it violates parity, right? It violates parity, and it's chiral, okay? It has a handedness to it. It has both of these things that are linked to each other. And so one of the things that we've been playing with here is whether or not actually gravity might actually have that property. And if we've never tested that idea, and it could be that we've been working with gravitational wave astrophysicists, my colleague Nico Yunez and others. We've been talking to, you know, gravitational wave astrophysicists, people who study black holes, AGNs, to see whether or not there might be hints of this parity violation in the gravitational force. So that's one example, I think, where we want to try to minimally develop a known theory like general relativity with this extra feature, and see what, you know, how much it can say about new observations or anomalous observations that have been made already. So yeah, we are in the business of engaging with observationalists.
Yeah, that sounds really exciting, because as you say, we have those unknowns, and we have some great data sets coming through. And we now are in this real-time multi-messenger world where we have everything from the dark sector all the way up across the whole of the electromagnetic spectrum. So I think you're right, it's a very special time observationally and experimentally. And I'm really interested to sort of think about the work that you've talked that you're doing on machine learning and dark matter. And obviously there are many of our audience members who are thinking about the dark energy problem. Why do we see that sudden acceleration when, I guess, the galaxies condense at, you know, that particular redshift? Is that a coincidence? Are we missing something fundamental about why we have this concept of dark energy? But of course, you know, machine learning is a brand new tool. We've got workshops at the conference this week. A whole new generation of scientists coming in and learning that. So really excited to hear about the work that you've been doing in that area.
Yes, no, it's exciting stuff. In fact, I mean, I get some credit for being like one of the first, if not the first person to introduce machine learning into cosmology. But back in 1997, I don't want to toot my horn, but so I'm revisiting my old self. Leon Cooper was my first PhD advisor, and we were studying neural networks back then when I was a grad student. And I moved into cosmology from trying to apply large-scale structure studies into machine learning, vice versa. And so it's exciting to me because the way machine learning and physics are actually linked is interesting. It's not, okay, there's machine learning as a tool of analysis for physics, but then there's something a little bit more interesting, which is this: if you look at machine learning architectures and statistical mechanics, the way actually the laws come together and emergent properties come together, you find that there's some interest in, obviously, connections. And I'm interested in those deep connections between, say, machine learning architectures and algorithms, and actually how the laws of physics actually interact, or maybe there's something deeper about the laws themselves, how the laws are learned. So if here's one silly idea that I'm working on right now with my friend Jaron Lanier and Lee Smolin. Jaron is at Microsoft. And the idea is, in a nutshell, think about the laws of physics as we know them, right? Now, how did the universe come up with the laws? So imagine that underlying those laws is actually a machine learning algorithm, right? That actually the universe actually is encoded with a machine learning algorithm, and it learns the laws through this algorithm, right? So the universe, there's an aspect of the universe that's a machine learning algorithm. Now, the substrate doesn't have to be that the universe is a computer. I'm not saying that, right? I'm not saying the universe is a computer. I'm just saying that the universe could learn the laws in the same way. By analogy, machine learning architectures are designed to do some forms of learning, be it supervised or unsupervised, or things like generative machine learning algorithms. But the point is that, can we like study the laws of physics and use that to come up with new machine learning algorithms, for example? So that's another. Can we develop new machine learning through the lens of physics, as we did like the Hopfield model, for example?
I think that's very Hollywood sounding almost, but I mean, it's really interesting to relate that to, I guess, gravity as an emergent property. I mean, is this an idea that you're keen on, or do you think that that's a useful way to go, or are we missing something there as well?
No, that's a very good question. That's a very insightful point you just made there. It seems that I've had the fortune, and also, if you want to say, I want to say problems that I've, as a cosmologist, I felt like I've had to talk to everybody that works in quantum gravity, not just string theorists, but people in quantum gravity, dynamical triangulations. Faye Dowker, my friend Faye Dowker, was one of, she has her own version of quantum gravity as well. And I talked to, I talked to everybody that I could, because all these ideas in quantum gravity, and what's interesting is most of them point to this idea that gravity is emergent. Yeah. That quantum theories of gravity, like, string theory, the idea of holography, again, is pointing to, in their toy models of the ADS-CFT correspondence, points to that. Even in loop quantum gravity, for example, you can make the case, and I'm writing a paper right now with Ron Friedel and my postdoc, again, pointing to that even in loop quantum gravity, four-dimensional gravity can be emergent from a three-dimensional quantum gravity system. So that's right. So the idea of emergence, in my third book, actually, my second book, Fear of a Black Universe, I formulate, I basically say, I make the case that physics is not complicated. All these things, you don't have to memorize any of these equations. You can take a bird's eye view, and I call it the jungle of physics, and see the entire jungle through the lens of three principles. And the third principle I talk about is the emergence principle. I upgrade that to a principle of all of physics. So I think that gravity is emergent, but the question is, what does it emerge from? I don't know the answer.
Yeah. So we should hook up with some condensed matter physicists as well. But I think that the from and the to is really important. So I've taken chair's prerogative and asked you all the interesting questions that I want to ask you, and I'm being quite ungenerous to my questioners in the Q&A sessions here. So there's lots of questions in about music, but one that's really struck me. You're talking about writing your third book. And I have a question here from Fiona Murphy Glacier asking, do you listen to music while you're writing, or do you need silence?
I do both, but I definitely listen to music. I am a big fan of I listen to a lot of classical music as well. I love Chopin. I love Beethoven. I love Rachmaninoff. I love Gabriel Fauré, the French Romantic. So I find that when I listen to an instrument I love string quartets. I find them very, it really creates a nice atmosphere. I, of course, listen to Brian Eno's ambient stuff as well. And I also like listening to birds in the background. Like here in the Caribbean, they have some nice tropical birds that make their own bird songs.
That's really nice. You're talking about the birds actually composing their music. Yeah, and I think there's another interesting question here, as I say, for all of our music aficionados in the audience, asking about what your thoughts are on the 12-tone equal temperament as a tuning system with its approximations for perfect fractional intervals. And I'm sort of struck by what you're saying about enjoying string quartets, where of course they will use different intervals depending on which instruments string musicians play with. So something I hadn't appreciated. I'd learned, piano as a child, but actually my son's learning violin, and his music teacher was saying, well, it depends who we play with. And so that's that idea of stretching a musical instrument, really stretching a musical interval, surprised me. And I thought, gosh, that's a very different way of using your ear, your brain, and getting things to sound right. So back to sort of the comments that you're making about those harmonics and all of those upper frequencies that sit with the main note. So what's your opinion on this 12-tone equals temperament, if you have one?
Yeah, My opinion is that I think, you know, it's an approximation for maybe something physiological. I mean, like, for example, there's another Carol who's a very, very, I mean, ingenious and famous music theorist and cognitive scientist at Cornell University. Her name is Carol Kremanskill. You should check her stuff out. She's done the physiological studies that somehow the brain does respond to some of these things. But the human voice is an example. If you listen to Arabic music or other forms of music, even like Eastern, like, you know, Eastern European, like folk music, the human voice does bend naturally. So I think it's both, you know, so I embrace it all.
Continuum rather than discrete.
I think one is like an approximation. Yeah.
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 Yeah, as we do in physics, actually, we have those approximations when we need to, depending on the multi-scale physics that we're studying. So we have a few minutes to finish. Yeah. And I think, you know, a couple of other questions that have come through. Again, there's lots about the analogy between music and physics. And it's incredible when we think of Einstein, of course, also was a talented musician. So there's something maybe fundamental about the way our brains work. And it almost takes us into that multidimensionality. What do you see as sort of, you know, your aspirations, I guess, for music and science in the future, particularly as our world becomes very complex with all these you know, I guess complex instruments, complex technology, you know, machine learning and artificial intelligence coming into every parts of our lives. And we're now talking about augmented human reality and how that will all interface with our physiology. It seems that we're reaching either a very promising time in humankind or actually quite a threatening time. What's your feeling around all of that?
I think, like, you know, I think Abdus Salam said it well. I think I have a lot of thoughts about that. My book, Fear of a Black Universe, a lot of it is about that conversation, actually. But I encourage all of you to, you know, to check that book out, or maybe in the future I'll give a book talk. Where I've spent the last 5 years writing that book, so it's very much in that book, right? But I would say one of the things I know inspires me is you know, Abdus Salam, who is, you know, whatever, a Muslim Pakistani Nobel Prize. He won one of the most important Nobel Prizes. At his Nobel speech in Stockholm, he said, "Scientific inquiry is a common heritage of humanity." So I think as we move forward and as we continue to move forward, we recognize that it is our common, it's a human heritage. Like languages, we all have different languages. Linguists will tell you that, you know, there's something that is, you're born as a human being, you have the capacity to learn a language, wherever that may be. You're not different fundamentally from another human being. And what Salam is saying is that if you look at scientific inquiry, the activity of human beings across our planet, the West, the East, Africa, whatever, if you look at the history, it is our common heritage. And therefore, it is our birthright to make sure that we create those opportunities. And again, this is not a charity case. I'm saying this comes from a place of respect that we you know, engage each other very seriously, and recognizing that all the different ways of engaging in the scientific enterprise, it is our common heritage, and we engage each other with strength and compassion and respect and high expectations. You know, I engage a very diverse and varied group at Brown as my students. They come from all different sorts of backgrounds. I expect more of them. They have to work hard. They have to, right? Because I think they're brilliant, and I bring that to them. I don't come at them as like, oh, you know, you had it hard. No, you know, it's our common heritage as human beings to forge forward in this great adventure called science. It doesn't belong to one group over another group, one gender over another gender, what have you. And I think we, moving forward, need to seriously engage with that great promise. And so it's in that, I think I'm inspired by Abdus Salam's statement. Scientific inquiry is a common heritage of humanity, or some kind of paraphrase, and you can look it up online.
Stephon, on that incredibly empowering, inspiring note, thank you so much for connecting with us internationally and in every way we have in this talk today. The variety, the richness, the many conversations that you will have started today for us that will continue, I hope, through the rest of our week and through our communities. And I know that we'll stay connected, and I hope we'll be able to host a book talk in the future. Thank you so much for your time, and it's been a real privilege and pleasure to connect with you today. Thank you.
I look forward to it. Thank you.
Thank you.